Okay. All right. How's everybody doing? Got a small group today. Must be Friday. Oh, let me get this on so you guys can see. Give me a second here to see if I can. Yeah. Yes. Okay. I think I need to share my screen. Yeah. Let me see. Hmm. Hmm. Um. Anybody know how you share your screen? Hey, Domi, hang up and call me back. Okay. Let's see. Where was the button? I did it one time already. Oh. Video. Okay. Whoa. Trippy. Okay. All right. So, okay. So let's start. All right. So last time we had started to talk about the degenerate electron gas. So this is a system of N electrons. So they're obviously identical. And these electrons are free to interact with each other, right? And they will interact with each other through the kind of a screened Coulomb force, right? And in addition to these electrons, we're dealing with a solid. So you can think of it as just a chunk of metal if you want. And so we'll have not only free electrons, but we'll have kind of a lattice of positively charged particles, which would be which represent the nuclei of this of this system. But the electrons are free to move around, and so we wrote down the Hamiltonian for this system. We broke it into three separate parts depending on whether or not the background was involved. So we wrote down the just kind of exclusively electron part, which was made up of the kinetic energy parts of the electron and their interactions. We broke it, and the other piece was contribution from the background by itself, right? The interaction of the lattice sites. And that thing we went ahead and computed because the number density represented by rho here is a constant, right? So the integral is doable. So we were able to pull out these factors of n over v. So we're assuming there's n lattice sites and the volume of the solid is v. And so we pull that out, and then we can do the integral after making a change of variables, and we get this, right? And we noted that we included this screening term. So it's really a Yukawa potential is what we wrote down. And so what we saw was the reason for that is because if we hadn't included that, this term would blow up, right? We would get an infinity, and that's never a good thing when you're talking about physics, okay? So we kind of regularized this integral by including this kind of screening term, and we found that we got an answer that went like 1 over mu squared. Now, mu is kind of a fake parameter that we put in by hand. So in the end, we would hope that, if we're doing real physics, at the end of the day, we should take mu to 0, right? And hopefully everything will be well behaved, right? That was our hope. And then finally, we computed the contribution from the interaction of the electrons and the lattice background. Again, that we could do that one because we could go ahead and compute it because rho is a constant again. And so we computed it, and we saw that it also went like 1 over mu squared, but it had an opposite sign, and we thought, oh, maybe it cancels off, but we saw that we were cancels off that previous term, but we saw that we were off by a factor of 2. So we still have this kind of divergent piece hanging around. Okay, and so when we put everything together, we had this, right? And then what we wanted to do was apply our second quantization formalism to these two terms. So the kinetic term, which is a single particle operator, and the Coulomb interaction or the Yukawa interaction, which is a 2-particle operator. And the lecture before, we had seen how we write those operators down in general. So in general, we would write down an operator for the system in terms of the individual operators and then our number operators, depending on what basis we're in. And for us, our individual operator is the individual momentum operator, and so it makes sense to work in momentum space, right? So that's what we did. But you also have to keep track of spins, right? Because we're dealing with electrons, so our state's not only specified by momentum, but it's also specified by the spin. So we went ahead and computed that thing, and we found that it just gives us h bar k, where here now k is just a number with some delta functions due to the orthonormality of these states. And so we're able to write down using just our, kind of our general formula for 1-particle operators, the operator for kinetic energy, right? And it makes sense because it's basically just counting up all the particles that have momentum k, and you multiply it by the kinetic energy of that state. Okay. And then next, what we wanted to do was consider the Coulomb or the Yukawa interaction. And so we had a general formula for that guy as well. It's a little more complicated because now we have basically 4 particles or 4 states that we're dealing with, right? We have 2 in the initial state, 2 in the final state. Okay. And so we plugged in what we had, and we noted that the potential is only depends on position coordinates, right? So we would want to, in order to evaluate that, it'd be nice if we could, hit it on position eigenkets. So we did that. So we inserted 2 complete sets of position states, right? That allowed us to evaluate that V and pull it out. Now it's just a function of these numbers that we're integrating over because of the completeness relation. But it gave us a number times all these things, and these things are nothing but plane waves, right? And we're working in what we call the big box approximation, so there's a normalization factor depending on the length scale of this box that we're in, okay? In the end, we take it to be infinity and hope that everything works out, right? Let's see, so what we do? So we worked this thing out explicitly, so I plugged in expressions for the plane waves, and then also included the factors for the spin. So these are the spinners that we talked about a couple lectures ago, and they're labeled by their particle. So this is lambda 1, so this is particle 1 spin, right? And we see that these guys, when they hit each other, this lambda 1 dagger and this chi lambda 3, are going to give us a delta function, right? So it's going to tell us that the particle 1 in the initial state or has to have the same spin as particle 3 in the final state. So it's a kind of a conservation statement that tells us that there's no spin flips, right? So this interaction doesn't induce any spin flips. So if you have an electron cruising along and another electron, and say this one spin up, this one spin down, they interact with each other, their spins remain the same. Right? You'll see if you go into quantum field theory that there will be cases where you'll have some interaction that will cause them to flip. I can't do it simultaneously. It's kind of like you guys do this. Oh, I can do it. But this thing. So they come in and then they would flip. I still can't do it, but you get the idea. Okay. So then we had delta functions for the spins, and then we wanted to compute these integrals, the x and x prime. So we made some change of variables. We were able to do one of the integrals. It's just the Dirac delta function, right? And it's a special Dirac delta function because it's telling us to conserve momentum, right? 3 momentum of the state, right? And that left us with one integral to do. And we could do that integral because we've done it before, right? We introduced the concept of the momentum transfer, which is just the difference between, say, particle 1's momentum when it's incoming into the interaction, and then when and then the momentum when it's leaving the interaction, I guess you would say, right? And so we were able to compute this matrix element. We got something that looks like this. Okay, so finally we put it all back together, and we got this thing, right? And it's still a mess. So we got it in terms. So we computed the matrix element. That's where these things came from, along with this factor. And now we've got to deal with these guys, right? But we still have this problem that's hanging around with the mu equals taking mu to 0, because this term still looks like it blows up, right? But we do have a factor of mu squared over here, right? So you could hope that maybe there's a case where when q is equal to 0, that these terms would cancel out, right? I don't want to go through the whole thing again, but that turns out to be the case. So we looked at the case where there's no momentum transfer, right? And this is just saying if there's no momentum transfer, there's no interaction, right? And so it would make sense that that this term that doesn't involve any interactions, which we don't care about, would cancel off a piece that kind of came about because of that we put it in by hand, right? And so that's what happens. So this thing cancels, and after some algebra with the annihilation and creation operators, and so we see that it exactly cancels. We're left with one term that goes like 1 over mu squared, but here we've got a factor of the volume, and so what we do, remember in this big box approximation, is take V or L to infinity, and if the range of the potential is small, which is what we have, it's just a Coulomb interaction or a screened Yukawa interaction, this thing's going to go to 0 faster than it blows up. So we're safe in taking these limits, L to infinity, mu to 0, and so that term drops out, and we're finally left with this thing, right? So we have a Hamiltonian that we're going to split into 2 pieces. One piece is just the kinetic term, right? And the second piece is coming from our interaction, right? So we're summing over the spins of the initial particles, or the 2 particles, and we're summing over their momentum and their sum or their difference. And this prime here reminds us that we've already accounted for the case where q equals 0. Okay, so we don't want to reintroduce that divergent term by considering q equals 0. So that's where we stopped. Okay, any questions on that stuff so far? Hopefully, if you haven't, you'll get a chance to work through it. It's a good exercise, especially if you're going into condensed matter or quantum field theory, because you'll do a lot of stuff like that. Okay, so what I want to do today is solve for the eigenvalues of this system, right? And what we did was we wrote it kind of in a suggestive form, h naught plus h1, where h naught is what I'm going to call the simple piece, and h1 is a complicated piece, right? But it's a complicated piece that goes like E squared, right? And E squared is a small number, right? It's a small parameter, and really we're taking volume here to be infinity, so it's a real, that prefactor is, or the factor out in front is really small. Okay, so what we can do is instead of trying to solve this thing exactly, we can use perturbation theory. Okay, and hopefully just first order perturbation theory, and we'll get a pretty good estimate of what the energy eigenvalues of the system are. Okay. So solving this problem exactly is like what they always like to say, beyond the scope. It's beyond the scope of this lecture. It's beyond the scope of my knowledge. But so we're going to use perturbation theory. Okay. And a lot of times when you tackle problems in the real world, you will want to, like our expression here, it comes in terms of E squared and V, but there will also be other factors like H bar and dimensionful, other dimensionful quantities floating around. And a lot of times what you want to do to simplify your life is to rescale things. And what you'll do, and this is for several reasons. One is just to simplify your life as far as the algebra is concerned. And then a lot of times, when you go to compute these things in real life, you have to, at some point, make the transition to numerical techniques. So using a computer, and computers don't like, when you have big numbers and small numbers and you're trying to integrate over things. Okay, so a lot of times it's good to rescale everything so you have everything basically on the same order of magnitude. Okay. This is I'm just going to show you a simple case where we scale. We're going to scale the variable, one of the variables, just for, like I said, just for convenience. But when we get into relativistic quantum mechanics, you'll see that we do a lot of weird stuff, which it's like setting C and H bar equal to 1, right? Just to get rid of them so we don't have to keep writing them. And then at the end, you multiply by, whatever the factors are, H bar and C, to get the dimensionful quantity that you're trying to compute. Okay, but it's just an example of physicists being lazy, really, because a lot of times you just don't feel like keep writing all these constants when, they're not really important until the end when you're trying to compute the number. Okay. All right, so one of the quantities that we're going to need is basically the density of the system, okay? And the density, or the number density of the system. The number density of the system is given by the total number divided by the volume, right? And the volume here, so what we're going to do is rescale this to the case of one particle, right? And the volume that particle sees, so that if we have, so if we have particles like here, like this, so I'm considering this particle. Okay, so the number density of this particle is 1 inside of this volume, right? And this volume is going to be, it's a sphere, so it's going to be 4/3 pi, and then whatever the radius is here, okay? And the radius, we're going to call R naught cubed, okay? So for one particle, the number density would be one particle over that volume, and so that's where this expression comes from, okay? So number density, I can write in terms of this R naught quantity. But what's this R naught quantity? Well, it turns out that a natural scale, if we're just dealing with normal, atoms, would be the Bohr radius. Okay, so the Bohr radius comes out of the calculation for the hydrogen atom, but it's a good order of magnitude type of parameter to use. Okay, so what we'll want to do is we're going to rescale this quantity R naught and rewrite it in terms of A naught. Okay, so we're going to define basically what's called a dimensionless distance scale. So this RS and RS. So here I'm writing R naught in terms of A naught times RS. Okay, so RS takes up the difference between A naught and R naught, right? But what I want to do is rewrite that thing in terms of RS. Okay, so RS is just given by R naught divided by A naught. Okay, and you'll see why we want to do this in a little bit later. Okay, so this is not something maybe on a first stab that you would do, but after you're done with the calculation, you go back and say, how can I simplify this so I can write it in a paper, and people will understand what I'm talking about, and how can I make myself look really smart in the process. And so you do things like this. Okay, so this is a rescaling that will simplify things, when we get to computing the energies and stuff. Okay, so what we want to do first is we want to compute the energy of the system. Right, we're going to use perturbation theory. So the first thing we need to do is compute the unperturbed energy, and we're going to work just strictly with the ground state. Okay, so assume that we've cooled this thing down to 0 T equals 0. Okay, so everything settles down. There's no fluctuations or excitations or anything like that. Okay, and to do this, we're going to introduce the concept of the Fermi energy of the system, and this is something that maybe you've heard of before, either in condensed matter class, but your stat mech class, or maybe what was the other one I was thinking of? Maybe you've seen it before. Okay, but so what we're going to do is introduce this concept of the Fermi energy. Okay, so we have a system of electrons, right? And if we cool this thing down, all the electrons are going to settle down into the lowest possible states, right? The lowest possible energy states, okay? And so what you'll have is, so we have energy levels. Say we start here, all right, let's label them by K, all right? So we label these guys by K, K1, K2, and there's a whole bunch of states that go up to K. That's called K little n, okay? Bless you, bless you. So as you fill in this thing, what's going to happen? Well, the electrons are going to pile in, right? But because of the Pauli exclusion principle, you can only put 2 particles per state, right? You'll have one that's spin down, one that's spin up, one that's spin down, one that's spin up, and then finally you would hit the end, right? And you would have your last electron, and it would fill up this final state, right? There's states above it, but they're unfilled, right? So they're empty. Right? So the concept of the Fermi energy is that the Fermi energy is this energy level, right? So this is what we would call Kf. Okay? So the Fermi energy is kind of the energy of the highest level, right? Or after you've, so it involves that's how I want to say it, okay? So as we fill up this, the energy levels are going to fill up to some maximum wave number or some maximum momentum or some maximum energy once you throw in some factors of h bars and m's, right? And so you can relate so you can state the energy of the system in terms of this energy level, K Fermi, okay? Make sense what I'm saying? Okay. Okay, so what we can do is we can relate this number K, or this wave number Kf to the total number of electrons, right? So if I measure Kf and I know the energy level and I know that 2 electrons can go in each state, I can figure out n, right? I could get n from K Fermi, right? And so that's what we're going to do. So, and the way you would compute that thing is by summing over all the energy levels, right? But all the energy levels are going to be, they're either going to, as you sum over, so forget about the spin for the time being. As you sum over the K, right, they can either be, the levels are either going to be 0 or 1, right? Because you can only put, if you think of it just in terms of momentum, you can only really put 1 particle here, right, per state, okay? So we can represent that by the step function. Everybody familiar with the step function? Works, okay, good. All right, so it's a step function in K, and it tells us that if we go above K Fermi, this is 0, right? Because we know that we fill everything up to K Fermi, and then after that, there's no particles in these states. right? The sum over the spin is just going to give us a factor of 2 because we can put 2 particles per state, okay? So in real systems, it's not going to be like this nice discretized, picture. It's going to be kind of a continuous band, right? So what we want to do is really convert this sum into an integral, right? And you should be familiar with how to do that from StatMech. So we're going to convert it to an integral over momentum or the wave number, right? So I still have my step function here, and I have my sum over spins. But when I make that conversion from a sum to an integral, I have to include this factor of v over 2 pi cubed. Okay, 2 pi cubed is just what's the word I'm looking for? It's just a convention, right? But the v is important because what it does is it cancels off the units of going from a sum to an integral, right? So this thing's going to have units of 1 over volume, right? If you remember the units of wave number. Anyways, so we convert it to an integral, right? And so what I want to do is do this integral, this k integral, and so I can break it into I can treat it just like a spatial integral, and I can break it into spherical coordinates, right? So I have some solid angle integral, and then I'll have some radial integral, right? And then my step function. And so then I can do this integral. It's easy because I've got this step function, right? And so it tells me that, I can integrate all the way up to, normally this integral would be from 0 to infinity. Should have written it in here, right? But because of the step function, it can only go up to k Fermi, right? So it's a finite integral, and even I can do this integral k squared, even though I get the wrong answer in the next line, okay? So the next line here, this 4 shouldn't be here, okay? So if you're watching at home or taking notes now, take note that this 4 is not there, okay? So if I integrate k squared, I get k cubed over 3. The factor of 4 pi is coming from the solid angle integral, and then I've got my factor of v over 2 pi cubed. And like I said, there's no spin dependence. There's no explicit spin dependence, so we can just do this sum, and it's going to give us a factor of 2. Right? So it's just accounting for the 2 spin states per energy level. Okay, so I can put all that stuff together, and I find that I can write the number of particles in terms of k Fermi, right? Or inverting it, you can write k Fermi in terms of the number and the volume, right, like this. So depending on what you're working with or what you're trying to compute, a lot of times you'll go back and forth between the number the number or k Fermi. Okay, and so I can plug in the explicit expression for the volume and get something that looks like this. And we'll come back and use this in just a minute. Okay. So I haven't computed anything, dealing with the ground state energy yet, but I am trying. I'm working there, and I'm trying to get some relationships that we can use to simplify our lives when we do. Okay. And like I said, 1 over k Fermi or 1 over k has units of distance, right? And we can see that 1 over k Fermi goes basically like the scale r naught. Right, this radius r naught, and that r naught is on the scale of the Bohr radius, and that Bohr radius is, I think it's 5 times 10 to the minus 11 meters. Does that sound right, or is it 14? I can't remember. You look it up. It's all right. The number doesn't matter.
It's 11.
It's 11. Okay, thanks. Huh?
It's half an angstrom.
Okay. I would not be able to tell you what an angstrom.
Oh,
how big an angstrom is.
10 to the negative 10.
Okay. All right, good. Okay, so that explains why the 5 comes in. All right, thanks. I've long forgotten any numerical values. As soon as I passed my qualifier, I was like, numerical constants are gone from my brain. Anyways, okay. So we're kind of in a position now where we can compute the unperturbed energy. Okay, so we're going to denote our state by this capital F ket, and the F I think just stands for Fock space. So we're in Fock space. Remember that where the ket is either, for fermions, it's either going to be 0 or 1, right? Depending on if the state is filled. Okay. And so we're going to use our second quantization form of the kinetic energy operator. And that thing is just the sum over K and lambda of our kinetic energy for some particular K and lambda. All right. And so what we're going to do is basically what we did just a minute ago in computing the Fermi wave vector or the Fermi momentum is, so we want to take this guy, this is our number operator, right? And our number operator is either going to be 0 or 1, right? So we can represent that again as a step function, right? Depending on if we're below K Fermi, then it would be 1. If it's above, it's 0, right? So I can plug that in. And that'll just, now it's just a number, so I can pull it outside of this sandwich between the bra and the ket. And we're assuming that these guys are normalized, so the inner product of these two just gives me a factor of 1. And so I'm left with something that looks a lot like what we had before when we were computing the number of particles in the system, right? It's just my factor of K here is different, right? I didn't have a factor of K actually before. Right, but so again, we're going to do this conversion from the sum to the integrals, right? So I replace the sum with an integral over d omega, where this d omega is in momentum space, and then I've got the radial integral in momentum space, and my factor of v over 2 pi cubed out here, okay? But we want to do the same. We want to do this integral again. Again, it's easy because this thing basically limits the upper limit to be K Fermi, and so you can do the integral, even though it looks like I had a hard time. So it's K to the 5th over 5, right? And then all these constant factors. Okay, so then what I can do is, so this should be K Fermi here. So what I do is multiply everything out, and I group things in a special way. So I can see that there's a factor here, V times K Fermi cubed over 3 pi squared. And that's just, if you go back and check our expression, that's just the number, right? The number of particles N, right? So I can write this expression for the ground state energy in terms of N, right? And what I have left is this stuff, okay? And so I have K Fermi squared here left over. And so the K Fermi squared, if you go back, I'm using this relationship here in terms of our R0 scale. Okay, so I'm replacing K Fermi squared with that thing squared. All right, so you see it would be R0 squared coming in, but I've rescaled it. Right, so now R0 is written in terms of RS and our Bohr radius. Okay, and the reason I do that, so this is a dimensionless quantity, this is a dimensionless quantity, is I want to see. Basically, I'm computing an energy, so I want to see something that has units of energy, and then whatever left over should be dimensionless, right? It's going to be multiplying something that has energy, right? And so that's what I get by doing this rescaling and reading and writing things in terms of N, is I get this factor out here, E squared over 2A naught. And if you remember, E squared over 2A naught is a number that you run into when you're computing the hydrogen atom. It's the 13.6 electron volts, right? So I have 13.6 electron volts, so that's energy, times the number, times some number, times another number, and then 1 over RS squared, and remember, RS is dimensionless. Okay, so it's just a scaling factor. So we get that the unperturbed ground state energy is 13.6 electron volts times this stuff. Okay, so that gives us, some confidence that we're doing things correctly, because at least we get the right units, okay, for the ground state. And that's always a good check, is to make sure you get the right units. Okay, so we've got the ground state, the unperturbed ground state energy. Now what we want to do is use perturbation theory and compute the first order energy shift due to our screened Coulomb interaction, right? And so I'll plug in H1, right, the operator that we had in second quantization, form, right? And here, again, I'm summing over Kp and Q, and the prime is telling me that Q can't be 0. and I'm summing over the two particle spins. I have 4 pi over the momentum transfer squared, and then I have the sandwich of our states, our ground states, on this operator, the string of annihilation and creation operators. Remember, these guys have subscripts that tell us that this annihilates a particle with momentum k and spin lambda 1. All right, and so you might think, okay, for a system of n electrons where n is large, this is going to be a hard thing to compute, but it's not. It's really not, because use the fact that this guy for fermions, the entries are either going to be 0 or 1, right? So you're using the fact that these guys have to obey the Pauli exclusion principle, and so that means if you could pair these guys up into a form where they look like number operators, then it's either going to be 0 or 1, right? It's going to hit the ket and return 1 or whatever, 1 or 0, and it leaves the ket the same, right? And then you would have the overlap of the ket with the ket, and that gives you 1, okay? So it's not like some complicated thing in the simple harmonic oscillator where you could have some string of you guys remember when we did, like, I had you compute like x to the 4th or something like that, right? And you remember that problem where you had strings of these operators, a daggers and a's, and it ended up being the only ones that were non-zero were the ones that had equal numbers of a's and a daggers, right? So this is kind of the same situation, okay? Right. So that the only way that this E1 is going to be non-zero, or a contribution to A1 or E1, is going to be if the A's and A daggers pair up. In other words, one A matches one A dagger. And by match, I mean has the same momentum and spin state. Okay? So in other words, if you go back and look, that means that, for example, here, so we have two possible spin states, right? Lambda 1, lambda 2 for our particles 1 and 2. So you see that this A, K lambda 1, so the spin has to be the same. So it's going to match up with this guy, right? Okay, so it's going to match up with this guy, but I know that Q can't be 0, right? That's what the prime is telling us, that we've already accounted for that. Okay, so what I have is I have to flip-flop that, right? So I have to, instead of taking this guy with this guy, I have to take this guy, the lambda 2, with this guy. Does that make sense? Right? Because Q can't be 0, so this guy and this guy are going to give me a contribution when they're paired together. So I have to pair the cross terms, if you will, right? So I have to pair the guys that have labels K plus Q and lambda 1 with the guys that have P and lambda 2. Okay, so that means that I can rewrite this stuff like this. So I have K and then K plus Q and K plus Q and K. So I've set P here to be K plus Q, right, in our expression that we had above. Right, and then from that point, it's just a matter of passing these guys through, right, because you want to write it in terms of a product of number operators. Okay, so these guys have different momenta, right? But they have the same spin, right? So if they have different momenta, that means that there's no, if you compute the anti-commutator of A and A dagger, so let me just write it. If I compute A and K, A dagger, K, right? If I computed this guy, right, this is 1, right? But if I give this guy a different momentum, K plus Q, then this is 0, right? So those guys commute, right? So that's where this minus sign is coming from. Okay? So the fact that they have different momenta means that they commute. Okay, they create and annihilate particles in different states. Okay, so I can move stuff around and get a product of two number operators. One that has that counts the particles that have momentum k and spin 1, and the other that counts particles with momentum k plus q and spin 1. Okay, and so I can write these as number operators, right? Or I can rewrite them in terms of step functions, right? So I can rewrite them respectively as this. So this counts basically the states that have, momentum, let's see, k less than k minus q, and or kf minus q, and this counts the states that have k below kf. Okay, right. The spin sum again gives us just a factor of 2, so I can just rewrite that as a factor of 2. And now what I want to do is convert those sums, so I have sums over k and q into integrals. All right, so that's going to give me 2 volume integrals in momentum space. Okay, and again, the step functions are going to allow us to do these integrals, right? It's interesting, I guess, to note that you can put this in a more symmetric form by introducing a new variable, this big P, right? And if you do that, then the arguments of the step functions are a little more symmetric. And in fact, you can show that this thing represents, this integral is just the intersection of 2 spheres with radii k Fermi. And their centers are separated by q. I don't know, that doesn't matter to me. I'm just looking to compute the number, but it's kind of cute. Okay. Anyway, so like I said, you can do these integrals now because you have these step functions, and what you get for the first order energy shift looks like something like this. Okay, and so this is after some algebra, obviously, right? But now I can add it to our unperturbed energy, right, which would like 1 over rs squared. Here I have 1 over rs. Remember, rs is dimensionless, so it doesn't matter that these guys have different, one's squared and one's linear. Okay, but again, we get something that goes like the 13.6 electron volts times some number, right? And what I've done is compute really the energy of a single particle, right, by dividing both sides by n. Okay, and that's the end of the day. So that is the first order or the calculation of the energy of our degenerate electron system up to first order in perturbation theory. Okay, in second quantization, right? So you would never, in your wildest dreams, ever want to try to do this using our single particle formalism. Okay, but but using the second quantization and our annihilation and creation operators, and imposing that the anti-commutation relations on them, which is basically manifestation of the Pauli exclusion principle, simplifies our life a lot, and you can actually do this calculation. Okay, if these were bosons, it would be very difficult. Okay, and there's actually ways of doing it, and that's what led to the Bose-Einstein condensate, which won a Nobel Prize. Anyways, so that's it. Next time we'll tackle quantizing the electromagnetic field. In other words, we'll basically quantize Maxwell's equations. Okay. Any questions? Concerns? No. Okay. All right. Well, have a good weekend.